ജിൽ സാർ ജോയിൻ ചെയ്തിട്ടുണ്ട്. ഗുഡ് മോർണിംഗ് ജിൽ സാർ.
Yes sir, yes sir. Good morning, good morning. സാർ അവിടെ എങ്ങനെയുണ്ട്, മഴ എങ്ങനെയുണ്ട്?
ഇവിടെ നല്ല മഴയാണ്.
ഇവിടെ നല്ല മഴയാ.
സാറേ ഒരു 2 മിനിറ്റ് കൂടെ കഴിഞ്ഞോട്ടെ, ആൾക്കാർ ജോയിൻ ചെയ്തുകൊണ്ടിരിക്കുകയാണ്.
ഒരു കുഴപ്പമില്ല സാറേ, ടേക്ക് ലോങ്.
ലക്ഷ്മി ടീച്ചർ തുടങ്ങാമല്ലേ ഇപ്പോൾ? മസ്ന കൃഷ്ണജിയോട് സ്റ്റാർട്ട് ചെയ്യാൻ പറഞ്ഞോളൂ.
A warm good morning, everyone. My name is Krishnaja, semester 1 student of Mathematics Department, Mother Teresa College. Let's begin the session with a silent prayer. Participants, please listen. I kindly request you to mute your audios and videos throughout the session for better experience. It's time to welcome everyone gathered here, for which I invite Dr. James Alexander, sir, Head of the Mathematics Department, Mother Teresa College. Sir, please.
Respected Dr. Mary Dorothy, Head and Coordinator of Academic Programs, Mother Teresa College. Distinguished guest and resource person, Dr. Jill K. Matthew. Respected teachers and dear students. It is my pleasant duty to welcome you all to this national webinar on approximation using Dirac sequences. This is the third webinar organized by the Mathematics Department of Mother Teresa College after the outbreak of COVID-19 pandemic and all academic activities shifted to the online mode. It is our conviction that this webinar will offer us an opportunity to learn the basics of approximation theory. Let me come to my duty. Dr. Mary Dorothy has graciously consented to inaugurate this webinar. In the absence of our principal, she has been offering able leadership in various academic activities of the college. Madam, we welcome you most cordially.
Thank you, sir.
It is with great pleasure that I introduce Dr. Jill K. Matthew to you. He took his PhD from National Institute of Technology, Calicut in 2016. From 2017 onwards, he has been working as assistant professor in mathematics, Mary Matthias College, Thiruvananthapuram. He has published more than 10 papers in international journals within a short period of time. Currently, he is guiding 4 PhD scholars. Dear Dr. Jill, on behalf of our college and all the participants of this webinar, I extend to you a very warm welcome.
Thank you, sir.
We also welcome the teachers and students from various other colleges, faculty members from other departments of the college, and our dear students to this webinar. I am extremely happy to welcome all the faculty members of the Mathematics Department, without whose sincere support and initiative this academic event would not have taken place. Thank you all.
Thank you, sir. To officially inaugurate the session, I invite Dr. Mary Dorothy, ma'am, Head and Coordinator of Academic Programs, Mother Teresa College.
Respected Head of the Department of Mathematics, Dr. James Alexander, our resource person, Dr. Jill K. Matthew, heads of departments and faculties of Mother Teresa College, faculties from various colleges and institutions, and my dear student participants. I am honored and glad to be present in this inaugural session of the webinar organized by the Department of Mathematics of Mother Teresa College. It's a national webinar on approximation using Dirac sequences. We all heard the academic achievements of our resource person, and we might have studied various approximations and applications in mathematics. But today, we are going to hear the approximation using Dirac sequences from an illustrious teacher. I'm sure that all the participants will be benefited out of this webinar. I take this opportunity to appreciate and congratulate the organizers of this webinar, the initiatives they have put in, and also the effort they have given to make this event a memorable one. On behalf of the whole Mother Teresa College community, and with the permission of all the participants, I inaugurate this webinar and I wish all success for this endeavor. Thank you.
Thank you, ma'am, for your words. We are eagerly waiting to the words of our distinguished guest. So without much ado, I invite our resource person to make the session more live and useful. Hearty welcome Dr. Jill K. Matthew, Assistant Professor of Mathematics, Mar Ivanis College. Over to you, sir.
Thank you. Good morning. Am I audible, sir?
Yes, sir.
Yes. Okay. Good morning, all. Respected coordinator and head of academic programs in Mother Teresa College, Dr. Mary Dorothy. Most respected head of the Department of Mathematics, Dr. James Alexander, sir. Program coordinator, Mrs. Masna S. All faculty who are attending this webinar and my dear students. Before I move on to my lecture, I wish to thank the program coordinator and head of the department for giving me this occasion to interact with great mathematicians of the future. In this 45 minutes lecture, my aim is to give you an idea about approximation of continuous functions by Dirac sequences and its advantages over other approximation techniques. Naturally, there are many approximation techniques are available in literature, and you have learned so many of them. So we are studying an approximation using Dirac sequences. So naturally, there must be some advantages and privileges over the existing techniques. Then only this talk and lecture will be relevant. Okay. So after the end of the lecture, you will be familiar with the approximation using Dirac sequences and some of its advantages. I think almost 80 to 90% of the audience are at the UG level. They are doing their graduation only. And remaining 10 completed their graduation. So as far as a UG student is concerned, this topic will be at a higher level. But I prefer this because when you listen to this lecture and try to answer some of the questions, your mathematical thinking capacity will be increased. It's an absolute truth. You can watch how the basic notions of analysis which you have studied are influencing higher mathematics. You can correlate many of them. For a smooth and better understanding, I divide this lecture into 4 parts. In the first part, I will concentrate on basics of approximation, where you can understand the need and what you have already learned about approximation. Here, I think the first and second year students can enjoy their best in the first part. In the second and third parts, I will concentrate on some background works. Background works means background for our study using Dirac sequences. Backgrounds are convolution and Dirac sequences. So in the second part, I will be concentrating on convolution, and the third part, I will be concentrating on Dirac sequences. In the last part, that is in the fourth part, I will use Dirac sequences to achieve our goal through convolution. So as most of the audience are UG, it's my duty to keep you all attentive. So naturally some questions and discussions will be there during the lecture to ensure only that all of you are following in the correct orientation. Okay, so with these words, can I move on to my presentation, sir? James, sir?
Yes, Yes.
Okay, sir. So I will share my screen. So, is it visible?
Yes, visible, sir.
Okay. So I start my presentation. In the first part, I start my presentation approximation using Dirac sequences with a question. What do you mean by approximation? What is approximation? So approximation, you might have heard about approximation in physics or any complementary courses or in your first, second semester onwards, you might have studied about approximation. Sometimes you have used the term approximation. So what is approximation? Approximation is just a compromise. A compromise between what? A compromise means it is an agreement, it's an adjustment. Compromise. It's a compromise between two things, a complicated thing and a simple thing. Okay, so handle complicated thing is very difficult. Okay, so actually we have to take a compromise between the complicated thing and the simple thing. That is, we are replacing the complicated matter by the simple matter. That is approximation. Okay. So many examples are available. You have studied from your upper primary onwards. That is, you have approximated pi. Pi is very much complicated number. Actually, it can be written very simply in a simple manner, pi, but it is very complicated. So the approximation you have used is 3.14. So whenever you write 3.14 instead of pi, actually you are using an approximation. Okay, so this approximation is being used from your upper primary onwards. Now, coming to college, a local replacement of a nonlinear smooth curve by a tangent at the center of the locality. So actually, you can replace by a smooth curve. Smooth means geometrical smoothness is actually analytical differentiability. You know all these things. Geometrical smoothness can be considered as analytical differentiability. So this locally you can replace a nonlinear curve. A nonlinear curve will enjoy some difficult properties. So it can be replaced. If you can replace by a smooth tangent curve at that point, then you can approximate that curve by the tangent. Clear? So all these works in your first and second semester. You are familiar with all this. Now, if you can replace a differentiable function by a polynomial of any degree. That is very important. You can replace a differentiable function, that is very differentiable, very complex differentiable function by a polynomial. The handling of polynomial or the dealing with a polynomial is somewhat easy. Rather than dealing with a differentiable function, it is not a polynomial, transcendental or like that. Dealing with that, those type of functions will be very difficult for us. If you replace by a polynomial, then study will be easy, clear. But there is an approximation, clear. So for the first and second semester students, for a better understanding, I prefer some few slides about polynomial approximation. Now, what is you are familiar with this question? Approximate f of x in the locality of x is equal to a. One requirement is that f of x is differentiable. Clear? Locality, you are familiar with a small neighborhood that is centered at a. Suppose if epsilon is the radius, then a minus. Any problem? Is there any problem? Madam, is there any problem? Okay, let me continue. Yes. Okay. So approximation of f of x in the locality of
Participants, please listen. Please. Okay, sir, continue.
Okay. approximation of f of x. F of x is a differentiable function. It must be guaranteed before the approximation. So f of x is a differentiable function. It's given, and you have to approximate it locally around around a point x is equal to a. That is, that approximation is valid only in that locality. Clear? That is, when you substitute a point in the original function and in the approximate polynomial, a point outside of the locality, then the answers will be different. Clear? They will not coincide it. So when you replace when you replace the original function and the approximating polynomial by a point inside the neighborhood, the answers will be same. Answers will be coinciding. That is the meaning of approximation. Local linear approximation. Clear? Not linear, necessarily linear. You can use a quadratic polynomial, cubic polynomial of any degree. Clear? In the first approximation, you are approximating this f of x by a constant polynomial. You know, a constant polynomial is a polynomial of degree 0, and the general format is p of x is equal to k. And you are using this p of x is equal to k as an approximate of this f of x. Clear? So naturally there should be an agreement. What is the agreement? The constant k is equal to, at the center they must coincide. At the center the original function is f and the approximating polynomial is p. Their value at the center must coincide. P of a is equal to f of a. Now what is p of a? The approximating polynomial is k. P of a is k. Always k. It's constant. So k is equal to p is equal to f of a. That is the technique in the first approximation. Now coming to second approximation, that is, you are using a linear polynomial for the approximation. Now what is the general format of the linear polynomial? K plus L into x minus a. K plus L times x minus a. That is the, since we are approximating at the locality near around x is equal to a using power x minus a. K plus L times x minus a. So here two agreements are there. K is equal to P of a is equal to f of a. Clear? Now come to the second agreement. L is equal to P dash a is equal to f dash a. Clear? There is a P dash and f dash. P prime and f prime are the derivatives, first order derivatives. So this is the necessity for the for first agreement. F must be differentiable. Since we are using derivatives in all our discussions, in the second approximation onwards, we will be using derivatives. So that fundamental requirement must be very essential. In the third approximation, that is approximation we are using a quadratic polynomial. The general form is k plus L times x minus a, or m into x minus a square. Not m by 2 is needed. M into x minus a square, where k is equal to p a is equal to f a, L is equal to p prime a, f prime a, m is equal to p double prime a, f double prime a. That is the agreement. Now you can approximate, for a particular example, approximate logarithm x, logarithm x near x is equal to 1. First you take the approximation of polynomial of degree 0. Then the agreement is p of 1 equal to f of 1 coinciding with k is equal to 0. That is log 1. You know it, log 1 is 0. Then that is 0. That is y is equal to 0. The x-axis is the approximation. So log x can be replaced by x is equal to 0, provided we must study in the neighborhood. We must proceed our study in the neighborhood of x is equal to 1 only. If you consider x is equal to 10, then this approximation is not valid. Clear? Now, whenever you approximate by a linear polynomial, the px is equal to f1 plus f prime 1 into x minus 1. That is, the polynomial is x minus 1. So you can use x minus 1 as the approximate near x is equal to 1. Clear? It is a better approximate. The accuracy will be increased. If you consider the x-axis and the line x minus 1, then x minus 1 will be very closer to log x in the neighborhood of x is equal to 1. That is the technique. Clear? Now, if you approximate using a quadratic polynomial, this is the technique. That is, x minus 1 minus x minus 1 square by 2 will be the quadratic polynomial. So, if you consider x is equal to 1, x minus 1 will be very closer to log x in the neighborhood of x is equal to 1 than x is equal to 0. naturally x minus 1 minus x minus 1 square will by 2 will be more closer than x minus 1 in the neighborhood of log x in the neighborhood of x is equal to 1 of log x. Clear? So you can approximate a cubic polynomial in this format. For a better understanding, I think I can use some GeoGebra backgrounds for a better knowledge. Let me take some time. Okay. So I plot y is equal to e power x. Y is equal to e power x. You know, x the natural exponential function is there. Y is equal to e power x. Suppose we are concentrating the neighborhood of x is equal to 0. Then what is the approximation? You know the Taylor-Maclaurin's approximation of e raised to x. That is 1 plus x by 1 factorial plus x power 2 by 2 factorial, etc. like that. So the first approximation is 1. What is y is equal to 1? Y is equal to 1. This is that curve. So in the locality of x is equal to 0, you can consider a small locality of x is equal to 0. That is, this curve can be approximated by, that is e raised to x can be approximated by the line y is equal to 1. Clear? But when you go forward or backward, backward of the point x is equal to 0, suppose consider a point y equal to 3. The curve is here or very much above the line x is equal to 1, but the approximation is not valid. But whenever you are in the locality, that approximation is valid, somewhat valid. It is not exact, it is approximate only. Okay, but when you come to the next approximation, it is somewhat y is equal to x plus 1. X plus 1. Now let us draw the curve. So it is more closer to our curve y is equal to e raised to x than y is equal to 1. Clear? So it's you got a better approximation. Now in the second approximation is y is equal to first 1 plus x plus x over 2 by 2. X power 2 by 2. Okay, so this is a parabolic curve. This curve is more closer to e raised to x than y is equal to 1 and y is equal to x plus 1. So the accuracy will be increased as you increase the power. Clear? So this is the basics of approximation. Now come to our slide. So you can approximate any differentiable function in the neighborhood of any point. You can select your point and any differentiable function, and you can take polynomial approximation which is valid only in the neighborhood of that point which you select. Clear? That approximation is valid only in that point. If you increase the degree of the polynomial, that is you go further and further, if you increase the degree of the polynomial, then that approximating polynomial will be more closer and closer to our original function. That is the technique of approximation. Clear? So I think from the degree first year students, second year students, all are following in the correct way. Now, in coming to the second part of my lecture, that is about convolution. It is a new product. Clear? The two functions f and g, and you can take the ordinary product f into g. How will you take f into g? Suppose f of x is equal to root x and g of x is equal to sin x. Then the natural product is fg is equal to root x into sin x. Clear? You can take composition. Root x and sin x composite is root of sin x. Okay, sin x and root x composite is sin root x. All those products can be taken. Clear? But it is a new product. It is convolution. Clear? Now, some requirements are there. So, in order to take the convolution product, you have to take two functions. One requirement is that those functions must be continuous. No need of the entire continuity. Piecewise continuous functions is enough. Piecewise continuous functions. Okay, so we take two piecewise continuous functions, and one more requirement is that f and g, if you take f and g, at least one of f and g vanishes at x whenever x tends to infinity. What is the meaning of that second statement? That is, if you take a function, suppose f of x is equal to 1 between minus 1 and 1, f of x is equal to minus 1, the value is minus 1, it is a constant function between minus 1 and plus 1, and whenever outside of that interval, minus 1 and plus 1, the f of x value is 0. That function is enough. That function satisfies the second property. That is, it vanishes whenever x tends to infinity. Clear? So if you take any finite interval and in the f of x assumes a value on that finite interval, outside of the interval, if it assuming 0, then there is no problem. That function is sufficient. Clear? So you take two continuous function, piecewise continuous is enough, and at least one must vanish as x tends to infinity. Clear? So in order, actually this second condition ensures to get a better, to get a finite result of the integral. Actually, coming to that formula, you will understand. The definition of the convolution is f star g of x. This is a notation. F star g is a minus infinity to infinity integral minus infinity to infinity f t g x minus t dt. That is, you replace x by x minus t in the first function x by t, in the second function x by x minus t, take the ordinary product multiplication times dt, that is integral minus infinity infinity f t g x minus t dt. That is the definition. Okay, so at least one must vanish out as x tends to infinity, then only you will be getting a finite integral. Clear? So here I am giving an example. So this is an example for a piecewise continuous function. In the piece 0 less than x less than 1, the function is assuming 1. In the piece minus 1 less than x less than 0, it is minus 1, but it is 0 everywhere. At x is equal to 0 is the middle point of minus 1, 1. The function is 0 there, and x greater than or equal to 1 and x less than or equal to minus 1, it is 0. Can you draw the graph of this function? Can you draw the graph of this function? If any paper or book is available with you, then you just draw the graph of this piecewise continuous function. Okay. This is the graph. Equal to 0, the function is assuming 0. At x equal to on 0 less than x less than 1, it is 1. In minus 1 less than x less than 0, it is minus 1. And everywhere other than this intervals, the function is 0. This is the nature. Okay, this is a piecewise continuous function. Now coming to g of the second function, g of x is equal to 1 minus x square. Now can you predict the nature of this function? Please respond, at least one of you. G of x is equal to 1 minus x square. Now can you predict which curve is this? G of x is equal to 1 minus x square. Is it a straight line? Is it a straight line? Please respond. Hello, am I audible? Hello?
Yes, sir.
Hello? Yes, you are listening. So, is it a straight line? G of x is equal to 1 minus x square? No, it is not a straight line. Straight lines are the functions with degrees 1, polynomials with degrees 1, clear? So, g of x is equal to 1 minus x square is not a linear, it is not a linear function, it's not a straight line. It is a curved line, curve, it is a curve. So actually what is that curve? It is a parabola, clear? It is a parabola. Now the parabola is downward. Now this is the plot of this parabola, g of x is equal to 1 minus x square. Now I am taking the convolution of the function f of x and gx. F of x was a piecewise continuous function, but g of x is continuous everywhere, and I am taking the convolution of f of x and gx, f star g. F star g will be 2x after the integration procedure, you will be getting f star g is equal to 2x. Now, what is the formula to get the convolution? F star g is equal to ft times g of x minus t dt. Clear? That is, there are two intervals, -1 to 0. In -1, 0, f is 1. Clear? Sorry, -1. So f of t is -1, it is a constant function, x minus t square dt plus 0 to 1, 1 minus x minus t whole square dt. Then after some manual calculations, you can get it is 2x. Clear? So you can do this calculation. I think it is best for you to enjoy this class. Okay, so f star g is equal to 2x, and if I plot this f star g, you will be getting a straight line which is passing through the origin 2x. Clear? F of x is f star g is equal to 2x. So it is continuous everywhere. Clear? So f was piecewise continuous, g was a nonlinear curve, but its convolute is a straight line. Clear? Okay, now another important result is that if you take all the piecewise continuous functions such that f of x tends to 0 as x tends to infinity, that means what? You are familiar with your normal distribution. You might have learned about the nature of the normal distribution. Actually, it is symmetric with respect to the mean mu. X is equal to mean mu. And as x tends to infinity or x tends to minus infinity, this f of x will tend to 0. Clear? That is the nature of that curve. Okay. So you consider all those type of functions. F of x, you consider all f such that f is piecewise continuous. F of x tends to 0 as x tends to infinity. Our previous example, you can take that f is coming under this collection delta. Okay, so you denote that collection by delta, and I am equip this delta with an operation. Clear? What is the operation? The operation which is familiar to you, f star g. Clear? So I take a collection. In that collection, all the elements are f. The two necessities to take the membership in that collection are f of x tends to 0 as x tends to infinity, and f must be piecewise continuous. So all those continuous functions will be naturally coming to this delta. Piecewise continuous functions will be there. Clear? So I equip this delta by an operation, equip this delta by f star g. Okay, now this star is bilinear. Now what is bilinear? F star g1 plus g2 is equal to f star g1 plus f star g2. Clear? That is, you are taking two functions g1 and g2, g from delta. That is, g1 is piecewise continuous and g1 tends to 0 as x tends to infinity. So you can take the sum g1 plus g2. You can take the convolute f star g1 plus g2. It will be same as f star g1 plus f star g2. Now, if you operate with the star on the right side, what happens? That is, you are taking two functions f1 and f2, f1 plus f2, sum of two functions, ordinary sum. You can take f1 plus f2 star g is f1 star g plus f2 star g. That is bilinear. That is linear in both directions, bilinear. Clear? Now, scaling also, there is no problem related with scaling. Scaling means that you can scale a function f. Suppose f of x is equal to x square. You can scale that. Suppose if the scaling factor is 2, then 2x square is the answer. You can scale in the reverse direction. You can take the scaling factor as -1. That is -1 times x square. That is the new answer. Clear? You can scale by 3.5 x square. So in general, the scaling factor is alpha f star g. Alpha is a scaling factor. It is a real number. If you are in real numbers, you can take real numbers. If you are in complex numbers, you can take complex numbers. Clear? Alpha. So alpha times f. It is a new function. It will be again a member of this delta, and g is already a member of this delta. Alpha f star g is equal to f star alpha g is equal to alpha f star g. Clear? That is there's no problem. Now coming to associativity, f star g star h is equal to f star g star h. All these are, there's no problem related with all these properties. Finally, f star g is equal to g star f. Now I am concentrating on that. F star g is equal to g star f. What is f star g? The answer is integral minus infinity to infinity f of t g of x minus t dt. Now what is g star f? G star of is equal to integral minus infinity to infinity g of t into f of x minus t dt. Now, can you prove that f star g is equal to g star f? Actually, it is a first degree, actually it is a problem which is suitable for a first semester students. Integral minus infinity to infinity f of t g of x minus t dt is equal to integral minus infinity to infinity g of t f of x minus t dt. Yes, you can prove both of them are same by the substitution u is equal to x minus t. You please note down that substitution. For the time being, I am leaving that proof u is equal to x minus t, and you can prove that f star is equal to g star f. All the other properties can be proven. Clear? So this delta I equipped delta with all the properties of an algebra. Clear? Now, algebra is a branch of mathematics. Before that, when you study further and further, when you are in the MSc level or final year BSc, you will be familiar with a collection of sets with an algebra that is we call that is an algebra. Clear? So this is all these are the axioms when in order to call a particular set as an algebra. Clear? So what is the present algebra? This delta is an algebra along with what? Under this star. It is a commutative algebra. Okay, commutative means it satisfies the commutativity property. Clear? Now my question is that this is the main problem. So this delta is a commutative algebra, or if you are taking R to take the scaling factor, if you are taking the scaling factor from R, then you can call this delta as a commutative algebra with respect to star over R. If you take the scaling factor from C, alpha from C, you can call this delta as a commutative algebra with respect to star over C. Clear? Now, what is the unital element in this delta? Now, is there any answer? Now, what is the unit element? F star something is equal to F. Okay. Now, if you consider the ordinary multiplication, now what is our identity? What is the unit element? F of x is equal to x square. And what is the unital element in order to achieve that? F of x into something is equal to f of x. The one function, identity, not identity function, the constant function 1. F of x is equal to 1 is the identity function. Clear? For the usual multiplication. Now, this is not the usual multiplication. F of star, F star something is equal to F. That is the any answer? Actually, there is no answer. There is no unit element of this algebra, but there is an approximating one. That is our aim of this lecture. Clear? Finding this unit element. After the end of the lecture, you will be familiar with that unit element, approximate unit element. Actually, there is no exact unit element, but you can find an approximate one. Clear? So, this is the now coming to the second Dirac delta function. Now, have you heard about the name of this scientist? Have you heard about anyone? Please respond. Do you know this famous scientist? Just make a guess. Yes, it is Paul Dirac. It is Paul Dirac who invented the Dirac delta function. Actually, he's a physicist, but we say he's a mathematician, British mathematician and physicist. He born on 8th August in 1902 at Bristol and died on 20th October in 1984 at Florida. He won the Nobel Prize for Physics in 1933. Actually, we are familiar with, we are fortunate with being an Indian. We are very, very fortunate to get two doctoral students who do PhD under his guidance. Do you know this person? He's a very famous scientist, Indian scientist. His name is Homi J. Bhabha, Indian nuclear physicist. He took his PhD under the guidance of this famous physicist, Paul Dirac. Now, one more mathematician is there. His name is Harish Chandra Mehta. He is actually an Indian, Indo-American mathematician and physicist. He is also well known for his famous works. Now, coming to this Dirac delta function. It is not an ordinary function. Actually, physicists use this function to represent an impulse. Clear? So this is the official definition for this Dirac delta function. Delta x is equal to 0 at x not equal to 0. That is the only point, at only point x is equal to 0, it becomes infinity. Now, my question is, can this definition, delta x, represent a function? Represent a function? All of you please respond. It is actually a turning point. Or can this definition of a delta x represent a function? You understand the definition well. At the only point x is equal to 0, the function takes the value infinity, but everywhere except x is equal to 0, it is 0. Clear? So my question is, hello James sir, can you hear me?
Yes.
സാർ ഇപ്പൊ കേൾക്കാം. സാർ ഇടയ്ക്ക് ലെഫ്റ്റ് ആയെന്ന് തോന്നുന്നു.
ഓക്കെ, എനിക്കൊരു പവർ ബ്രേക്ക് ഉണ്ടായിരുന്നു ഇവിടെ. ഓട്ടോമാറ്റിക് ആയിട്ട് നമ്മൾ ഈ UPS-ലേക്ക് ഷിഫ്റ്റ് ചെയ്യുമ്പോൾ ഒരു ചെറിയൊരു ബ്രേക്ക് ഉണ്ടാവും. അതുകൊണ്ടാണ്. ഇപ്പൊ പ്രോബ്ലം ഇല്ലല്ലോ?
ഇല്ല.
ഓക്കെ, സോ actually this is the definition of Dirac delta function. Now, being a mathematician, my question is that this delta x represent a function. This definition can represent a function. That's my question. This is the nature of, this is the plot of this delta x. Now, as a mathematician, this is not a function. A function means that it should satisfy the famous vertical line test. That is, if you draw a vertical line, then it must intersect the graph of the function exactly at one point. Then only you call that function as a.
Presentation കാണാൻ പറ്റുന്നില്ല.
Okay, sir. I will share. No, I think it is okay now.
Okay.
Okay, then there is no problem. This is the plot of the function. This is the plot of delta x. Clear? So we mathematician do not call this delta x as a function. Why? We call a function delta x. We call any function, any formula, any graph as a function whenever or only when, if you draw a line, vertical line, it should meet exactly at one point. Clear? So here delta, when you draw the graph, a vertical line parallel to, through the line y-axis, through the line x is equal to 0, then it intersects the graph at infinity many number of points. So our official, this is not an official definition for a function, and so it created a lot of disturbance in the mathematics community from 1930 to 1940. Actually, mathematicians never enjoyed this definition. They didn't consider this delta x as a function. Clear? So, the official legalization of this function as a function was made by Laurent Schwartz. He is a French mathematician born on 5th March 1515 in Paris, died 4th July 2002 in Paris. He won the Fields Medal. It's actually the Nobel Prize for Mathematics in 1950, and he called Dirac delta as a distribution or generalized function. Even though in mathematics background it is not even a function, but he legalized with the definition. It is actually the origin for the calculus of distributions. Okay. Now, what are Dirac sequences? A sequence means a collection of an even number in a number of functions, an infinite number of functions, countably infinite number of functions. Clear? So Knx is a sequence of functions. Kn from each Kn is from R to R such that Knx should be greater than or equal to 0. Each member of the sequence must be greater than or equal to 0. And when you integrate from minus infinity to infinity, the value of Knx is equal to 1 for all n. Clear? So this is now the third property is that for each epsilon greater than 0, there is a delta greater than 0 such that you can read it. But as in a layman setting, the area under y is equal to Knx becomes more and more concentrated at the origin. That is the meaning of which can be understood by a layman setting. Clear? So the first property is that Knx greater than or equal to 0. And whenever you integrate from minus infinity to infinity, the area under that curve should be 1, and the area must concentrate towards the origin, clear as sentence, to infinity. So if three conditions are okay with the sequence, then that sequence can be considered as a Dirac sequence. Now this is a rough plot for a Dirac sequence. Now Knx, it satisfies all the first property, Knx greater than or equal to 0. When you integrate minus infinity to infinity, the area under this curve will be 1. And when you go when you consider k1x, k2x, k3x, etc., you are going like that. As n tends to infinity, k1000, k10,000, many infinite number of functions are available with you. K1 lakh, k1 crore, k10 crore, etc., like that. So the area under y is equal to Knx, for getting more and more concentrated at the origin as n tends to infinity. Okay, so these three conditions are okay with this plot. So this plot represents a sequence of a sequence, and you can call the sequence as Dirac sequence. Okay, you can form any sequence, or you can make any sequence satisfying the first two properties as Dirac. Clear? I will come to that point. So from this plot itself, you can call all Dirac sequence consists only of even functions. Even function means what? You can call a function even. F of x is an even function when f of minus x is equal to f of x. F of minus x is equal to f of x. That is, it must symmetric with respect to the vertical line x is equal to 0. Clear? So all Dirac sequence consists only of even function. Now, these are some examples. Knx is equal to n by y times 1 plus n square x square. This is one example. Now, this satisfies all the properties I said earlier. Knx greater than or equal to 0, integral minus infinity to Knx dx is equal to 1. Now, how will you get that? Integral minus infinity to infinity n by pi into 1 plus n square x square dx is equal to 1. Yes, you can use the substitution. Nx is equal to u, and use that substitution minus infinity to infinity. Knx dx is equal to 1. You can prove that. Now, coming to the next sequence, if kx is any function with two properties, with the first two properties, kx greater than or equal to 0 and integral minus infinity to infinity kx dx is equal to 1. That is, the third property is not satisfied. This function kx only satisfies the first two properties. Clear? Then I can construct a new sequence which is a Dirac sequence from this function. How will you construct that? It is very useful. Knx is equal to nknx. Clear? So in the actually the variable is replaced by nx, and you multiply with a number n. That is a sequencing number. Clear? Knx is equal to nknx is a Dirac sequence. Now, our famous Gaussian distribution in statistics, you might be familiar with this function Gaussian distribution. Kx is equal to 1 by root of 2 pi into e power minus x square by 2. It is a Gaussian distribution. Now here you can it satisfy all the first two properties, kx greater than or equal to 0 and integral minus infinity kx dx is equal to 1. Now you form a new sequence, knx is equal to nknx. By this formula, it corresponds to a Dirac sequence. Clear? So if you are provided with a function kx satisfying kx greater than or equal to 0 and integral minus infinity to infinity kx dx is equal to 1, then from that function you can form a Dirac sequence. Now, Now all the ingredients are ready. Now I think time is over, but I will take some 10 to 15 minutes. Sir, is it okay with you?
Okay. Take your own time.
Okay, sir. Okay, thank you. Now all the ingredients are ready. Just wait, sir. Okay. Okay, sir. Sorry for the disturbance. Now I think it is visible. Am I right?
Yes.
Okay. Now all the ingredients are ready. We are at this moment, we are familiar with the convolution and Dirac sequences. Now we are searching for our unit element in delta. Actually, you might have remember that slide. Delta is the set of all collections, set of all functions which are piecewise continuous and tends to 0 as x tends to infinity, and it forms a commutative algebra. And you can find, my question is that can you find a unit element in that algebra? Actually, it is no, you cannot find a unit element for that commutative algebra, but you can find an approximate one. Clear? Using this convolution techniques and Dirac sequences. Okay, we use the first ingredient convolution to get an approximation, and this is the statement. This is the general approximation theorem. Let f be a bounded piecewise continuous function on R, and the sequence Kn star f. You are familiar with this star. Okay, so a bounded piecewise continuous function is there. F. It is not linear. It can be any function. The only two properties are it should be bounded. It should be bounded means that it does not go to infinity. Whenever you replace x by a particular value, you will be getting a finite value. That's modulus of f of x less than infinity. You are we mathematicians denote bounded functions like that. F b is a bounded function. It is a piecewise continuous function. And one sequence is available with you, that is the Dirac sequence. And now you take this convolution of Kn and F, that is K1 and F, K1 star F, K2 and F, K2 star F, K3 and F, K3 star F, etc. And that sequence converts to what? F. That is the general. So you can use Kn star F as an approximate of F. Clear? You can use K2 star F as an approximate of F in a better accuracy. You can use K3 star F as an approximate of better accuracy than K2 star F. Clear? So have you identified the unit element? Now Kn star F limit tends to infinity, Kn star F is equal to F. So what is that unit element? Each Kn is acting as the unit element. So you can take any Dirac sequence and any member belongs to that Dirac sequence is acting as the unital element of that algebra. Clear that? Okay, now so I'm going to this proof Kn star f minus f of x. Our idea is that actually we have to prove that Kn star f minus f less than infinity. So Kn star f minus f. Actually, I'm proving that the distance between Kn star f and f is less than a very small quantity. In that way you can get the proof. It is very simple, and there are lots of applications for this general approximation theorem. First one is Weierstrass approximation theorem. Here we are using the Knx. Kn actually Kn is a Dirac sequence. This is the Dirac sequence. What is the Dirac sequence? 1 by Cn 1 minus x square power n in minus 1 less than or equal to x less than or equal to 1, where Cn you have to take it as minus 1 to 1 minus x square times n dx. If you proceed with this Dirac sequence, then you will get Weierstrass approximation. Similarly, when you consider another Dirac sequences, you will be getting Fourier series, harmonic functions, heat, kernel on the real line, etc. Or many applications actually This is a series of talks. Actually, this topic is for consists of in my knowledge, 10 lectures will cover this topic here. This advantages of Weierstrass approximation. Now, one more theorem in literature is that the Stone-Weierstrass theorem. Every continuous function defined on closed interval AB can be uniformly approximated by polynomial. It is already in the literature. This is Stone-Weierstrass theorem. Now, in this lecture, we have proved that using Dirac sequences, you get a polynomial approximation. That is Weierstrass theorem. Clear? Actually, you must notice the difference. In the general approximation theorem, you can approximate f to kn star f. You can approximate any bounded piecewise continuous function to kn star f. It need not be it need not be a polynomial of any degree. But when you have to get, the basic requirement is that when you have to get the approximation as a polynomial, you must use what? Knx as a Dirac sequence as this particular kn. Clear? Okay, Weierstrass approximation. In Weierstrass approximation, you are getting the polynomial. You are getting the approximation as a polynomial. Now, in Stone-Weierstrass theorem, actually, you are also getting a polynomial. Then, what is the difference between our approximation using Dirac sequences and your in Stone-Weierstrass theorem? In Stone-Weierstrass theorem, that is the short form SWT, I am using it. SWT gives no information about the approximating sequence. Clear? But when you use the Rendu kernel, that is KNX, using Dirac sequences, each approximate, you know it. Without 100% accuracy, you know it. That is K1 star f is the first approximate, K2 star f is the first approximation. You can predict it, K2 star f. But when you use in the Stone-Weierstrass approximation theorem, you cannot predict the approximating sequence. Clear? And the degree can also be predicted here. These two are the advantages of this approximation using Dirac sequences. Clear? Now, I am binding this lecture. You can contact me at any time. This is my mobile number, WhatsApp number. This is my email ID, jill.matthew@mic.ac.in. Now, thank you for your patient listeners. May God bless you. And one thing I have to advise is that be true learners and true lovers of mathematics. Be true learners and lovers of mathematics. Okay. Thank you. Thank you, sir. Thank you. If any questions are there, then
Participants, if you are having any doubt, please unmute and ask. Or else you can put in the chat box. Feel free to ask.
actually, sir, if enough time is available, then so can you see my slide? Can you see my slide?
Yes.
Screen, okay. So, my summary of the summary of my lecture is Kn is available with you. Knx is available with you. Knx greater than or equal to 0 and integral minus infinity to infinity Knx dx is equal to 1. And the area is concentrated area under Knx is concentrated at the origin. That is, as s extends to infinity, it is very close to the x-axis. These three properties are okay with a particular sequence. You can call this sequence Knx as a Dirac sequence. Clear? That is one ingredient. Construction of the Dirac sequence. Now, suppose our question is f is to be approximated. F is to be approximated by a polynomial. Now, two conditions satisfied this by this f are f must be bounded. F must be bounded. Now, f must be piecewise continuous. F must be piecewise continuous. No differentiability is not needed. Clear? No differentiability. In our earlier case, I mentioned it in the first and second slide. I think it is correct. It is the first and second slides. There was an approximation. Actually, in that approximation, one thing is to be needed is that f must be differentiable. But here, there is no need of differentiability. Only piecewise continuity is needed. Clear? So that type of f is given. And you have to find an approximation. Now, what is that approximation? K1 star f is the first approximation. K2 star f is a better approximation than K1 star f. And K3 star f is a better approximation than K2 star f. K4 star f is a better approximation than K3 star f, etc. The approximation. Finally, this limit tends to infinity. Kn star f is tending towards what? Exactly tending towards this f. Clear? That is the approximation using Dirac sequences. Okay, this is the general approximation theorem. If you are using Kn by the Lendu kernel, LANDU, Lendu kernel, I use that formula in my slide. Knx is equal to 1 by Cn times 1 minus x square the whole power n in minus 1 less than or equal to x less than or equal to 1, where Cn is equal to integral minus 1 to 1 minus x square. If you use that kernel for this approximation, you will be getting what? Polynomial approximate. Each K1 star, Kn star f will be a polynomial. So, if you need polynomial approximation, you must use what? Kn. In the Dirac sequence approximation. In Fourier series, you can use that. In harmonic analysis, you can use that. In heat kernel on the real line, you can use that. Clear, etc. All those are applications using for this approximation using Dirac sequences. Clear. This is the summary of the lecture. Many approximation techniques are available in literature. You are studying some of them, but the most beautiful and the most useful, most powerful approximation technique is approximation using Dirac sequences. Okay. Sir, I think it is clear. If you have any doubt, you can ask me.
Hope nobody's having a doubt regarding the topic we discussed. So, thank you so much, sir, for this wonderful informative talk. Thank you so much. I request all the participants of this webinar to fill the feedback form using the link provided in the chat box, WhatsApp group, and YouTube live streaming comment box for availing e-certificates. So with that, we come to the end of the session. It's time to acknowledge each and every one of you for sharing your attention and valuable time with us today. Let me call upon Ms. Nancy VP of H2 Mathematics to deliver the word of thanks.
God. Gratitude is not only the greatest, it's such an honor for me to have this opportunity to deliver the word of thanks on this occasion. First of all, I would like to thank our respected principal, Dr. K.M. Francis sir, who couldn't attend this webinar but provided us all moral support for conducting this webinar. I also extend my gratitude to Dr. Mary Dorothy ma'am, Head and Coordinator of Academic Programs, Mother Teresa College, for gracing today's webinar and delivering the inaugural address. Thank you so much, ma'am. Now, I must mention our deep sense of appreciation to Dr. Jill K. Matthews, sir, Assistant Professor, Department of Mathematics, Mar Vanias College, for giving an excellent coverage on the topic, approximation using Dirac sequences. Thank you, sir, for inspiring and encouraging with your talk. It gives me immense pleasure to thank Dr. James Alexander, sir, Head of the Department of Mathematics, for organizing such an informative section even in the middle of this pandemic. On behalf of Department of Mathematics, Mother Teresa College, I would like to thank teachers and students from our college as well as from various other colleges for their active participation. Once again, I thank one and all for your cooperation in making this event a resounding success. Thank you.
Thank you,
Thank you,
Jilsa.
Ansi. I remind everyone to fill the feedback form. And
Thank
once
you,
again,
Nancy.
thank you so much for making this so much. Thank you. Thank you, sir.